Hello and welcome to section 6.1, Area Between Curves. For this section we are going to be using definite integrals, and instead of finding the area under a curve and between the x-axis, we're going to be finding areas between two graphs. So for this lesson you're going to need to remember how to describe regions in the plane between two graphs. So for example, this red graph is f of x equals e to the x, and this blue graph is minus e to the minus x plus 5. The region in the plane between these graphs is described by all the points between the x values where these graphs intersect, and all the y values that lie in between this top graph and the lower graph. So you should have seen how to describe these regions and how to work with these regions somewhat in pre-calculus. To find these points of intersection, you want to solve for x when you set the functions equal to each other. The solution to this equation is going to be minus 1.567 and 1.567. And the way to describe this green shaded region with set notation is like this. You don't really need to worry about creating that yourself, but understanding it. That means that is you have a region in the plane, a whole collection of ordered pairs bounded by graphs. So remember that the definite integral for a positive function gives us the area under the curve and above the x-axis for that function on some x interval. And also remember that the net area, when a function has parts below and above the x-axis, the net area gives us the sum of the positive area above the x-axis and the negative below the x-axis. So now let's look at the area between curves. And we're going to start off by looking at curves that are both regions both above the x-axis. So this upside down parabola is f of x, and this blue parabola is g of x equals x squared, and we're looking at the interval minus 2 to 2. Look at this green shaded region between the two graphs. We want to get that area. So notice that really what we're interested in, even though the interval given to us is minus 2 to 2, the area between the graphs that we're interested in is really bounded by, instead of minus 2 on the x-axis, this point of intersection on the left, and instead of 2 on the x-axis, this point of intersection on the right. So we're going to need to solve to see where f of x is equal to g of x to get our limits of integration. So let's think back to what the definite integral, how we derived that being the area underneath a curve. We used rectangles where the top of the rectangle was our graph of our function and the bottom of the rectangle was the x-axis. We're going to build on that, but instead of the bottom of our rectangle being the x-axis, the bottom of our rectangle is now going to be the graph of the given function that's below the other function. So what we're going to be doing is summing areas of rectangles where the top lies on f of x and the bottom lies on g of x. And notice we're just interested in x values between minus square root of 2 because that's where f and g intersect, and square root of 2. So how can we get that region, which I'm calling R, how can we get the area of that region from the integrals involving f and g? That's what we're going to be doing. So I've drawn some vertical lines through minus x equals minus square root of 2 and x equals positive square root of 2, since those are our real intervals that we're interested in between minus square root of 2 and square root of 2. And if we now look at the area underneath f, it's this purple region, and you can see that if we turn on the region R between f and g, the area underneath f contains the area between f and g, But it also has this overlap, this area down here, this purple area that's below G, that we don't want to include in our area for R. So if you look, what we want to do is take the area of just this part of the rectangle, but not this part of the rectangle. So if we take the integral under the definite integral to get the area under f of x, and we subtract the definite integral under g of x, that's giving us this rectangle, the area of this rectangle, minus the area of this rectangle under g. So that's how we get the area between the curves. We take the integral, the definite integral of f of x, and subtract the definite integral of g of x on that interval. So you can see that by those rectangles, summing the rectangles under f, and then subtracting the sum of the areas of the rectangles under g, is going to give us rectangles that just go between f and g, which is what we want. We want just the area of this region R. So in this case, the area of the region R is the definite integral from minus square root of 2 to square root of 2 of f of x minus g of x. F of x was minus x squared plus 4. G of x was x squared. When I find that definite integral, this is my area. To generalize, to find the area of a region bounded by curves between some vertical lines, x equals a and x equals b, where one graph is always above the other graph on that interval, we use the definite integral of the difference. Notice that in this example, we didn't have vertical lines given to us explicitly. To figure out where to integrate, we found the intersection, the x values of the intersection points of f and g. So even though the original problem said minus 2 to 2, we were just looking for the area between these curves, and that's bounded by their intersection points. So that's one thing to note, that f was completely above g on this interval minus square root of 2 to square root of 2. So that example was a case where both graphs are above the x-axis. Now if we look at a more general case where one graph's above and one graph is partially below, let's see if we can still do the same thing. It turns out we can. So again, I've just changed my g of x. I moved it down some, so it's x squared minus 1. So part of it's below the x-axis, but part of it's above the x-axis in this region. To find out what our limits of integration should be, so I set f of x equal to g of x and solve for x, and I get plus or minus square root of 5 over 2. So these will be my limits of integration. What I want to do again is to sum those areas of those rectangles. So can we do the same thing as before now that we have part of g below the x-axis? Well, again, if we turn on the area under f, we see that for this rectangle here, we want to get rid of that overlap, so in the purple area here. So we would take the rectangle under f and subtract the rectangle under g, like we did before. But then for the rectangles bounded by g below the x-axis and f above the x-axis, since the values of g underneath the x-axis are negative, when I subtract a negative, I'm adding. So for this representative rectangle, I get the area of this rectangle above the x-axis and plus the area of this rectangle below the x-axis. So in other words, it does work out. It doesn't matter if one graph is below the x-axis or not. As long as the one graph is above the other graph on the interval you're interested in, you can always find the definite integral of the difference between them to find the area of the region.